Next one up is Fernando Gonzalez-Zalba from Cambridge University / Quantum Motion.
Hi, good morning, everyone. Thank you for the invitation. I would like to start saying that I come in representation of the field of silicon-based quantum computing, and I'll be giving you an overview that at least partially challenges one of the theses that Oliver stated this morning, that the future of computing may not look like silicon. I do believe, and the field I work in believes, that quantum computing may be enabled by the same technology that we have in our microprocessors, telecommunication circuits, and memory devices, that of the technology of silicon. So the outlook of the presentation is, well, first of all, tell you a little bit about quantum motion, then the vision behind silicon, tell you a bit about the state of the art of the field, and flash a couple of results from our company. First, Quantum Motion is a UK startup focused on developing silicon-based quantum computing hardware, and we have several areas of coverage. The primary one is industry manufacturable quantum circuits, but as well, we work on the area of cryogenic electronics to support the development of any kind of quantum hardware, as well, for example, the space industry. And also, we have a small area dedicated to the development of algorithms specific to our hardware. This can only be done in a large team, so we are more than 50 people covering particularly the areas of quantum hardware, but also we have integrated circuit designers that come from industry that can translate our ideas into layouts that can be manufactured at scale. We also have machine learning experts and quantum algorithm designers specific for our hardware. And after our Series B early this year, we are the largest funded silicon-based quantum computing startup in the world, as well as the largest funded quantum technology startup in the UK. Good. So quantum computing, what is it? We've been talking about it. It basically uses some basic concepts of quantum mechanics, such as superposition or entanglement, to allow us to compute with exponentially larger resources. We've been talking about, for example, that with quantum computers, we will be better at factorizing large numbers, which is essential in online security. We will be better at searches in unsorted databases, ideal for the big data era, and we will also be better at optimization problems, which are used in the financial sector, as well as weather prediction, for example. But from a physicist point of view, the most beautiful use of a quantum computer will be in the design of new materials, new molecules, and new medicines through the exponentially larger computational resources of quantum computing. But for me, and I think for the field, the biggest challenge for quantum computing is to build the hardware that will allow us to perform any of those algorithms that we've just mentioned. Because without hardware, there will not be quantum computing. Some of the implementations that are being developed, you see them on screen, like superconducting qubits, Majorana, ion traps, photonic, and spins in semiconductor quantum dots, which will be the topic that I will be talking about. Particularly, we need to think in terms of the markets that we will be unlocked, but with the hardware that we have out there at the moment, we don't have enough computational resources to unlock any of the markets that we may be interested in, like energy, the financial sector, optimization, artificial intelligence, or pharma. Just to give you an idea of the size of the hardware, this is in terms of qubits per $1 million. At the moment, all technologies sit in the discovery phase of quantum computing. We need to scale up. We need more qubits and good qubits. But for a minute, let me ask you a question. What do these items that you see on screen have in common? Any taker? Exactly. They have all been superseded by modern technologies. Modern technologies, particularly based on the silicon transistor, such as the microprocessor, the CMOS sensor, digital circuits, solid-state memories. So what we find in history is that when you can perform a functionality with silicon, it will be the way it's done. So the question that we try to answer at Quantum Motion is, can we develop and implement qubits and quantum computing using transistor-based technology? Because if that's the case, given that there is no other technology in the face of Earth that can get close to match the levels of complexity and integration that industrial silicon technology has been able to achieve, it will mean a major revolution for the field. Just to give you an idea of the level of integration, on the latest Apple processor, we have more transistors than people on the surface of Earth. And in all flash memories, we have more transistors than stars in the Milky Way. Good, but it's not about all technology. Silicon also offers substantial physical benefits. We've been talking about isotopically purified silicon, silicon-28. Spins, and particularly the spin of electrons in that system, has one of the longest coherence times or quantum memory times of any material in nature. Silicon spin qubits can be operated at elevated temperatures. We are talking about 1 and 4 Kelvin also, but that makes a difference when we compare it to other implementations that necessitate tens of millikelvin or so, because we can combine them with classical electronics that need sufficient cooling power in order to work. And probably most importantly, as we've just mentioned, some of the devices that have been produced out there in academia very much look like transistors. So what's the state of the art? On the top row, we have 2-qubit processors that have been produced over the last couple of years by several teams across the world. Also, last year, there were demonstrations of 3-qubit processors that show error correction, particularly phase flip error correction. And the largest scale quantum processor that's been demonstrated comes from QTech in Delft with up to 6 qubits. These are all academic devices showing particularly high performance. Normally, when we try to specify the parameters of a quantum processor, we talk in terms of the initialization fidelity of those qubits, how you can operate on them with single and 2-qubit gates, how accurately can you read them. And as you can see, all the specifications are above 99%, which is the target for quantum hardware developers to perform error correction. And even in a single device, those numbers are approaching 99% and are relatively competitive with, for example, the most famous Sycamore quantum processor from Google. So what's the path forward? I think the majority in the field agree that there's a necessity to translate the devices that have been manufactured in academic settings to industrial processes to increase the yield and increase reproducibility, to leverage the semiconductor infrastructure to manufacture large-scale circuits, not also for quantum computing, but also to allow integration with classical electronics. Good. And this challenge is being taken forward by some companies and institutions out there, such as Leti in Grenoble, showing the first spin qubit in a device in 2016, and IBM and Intel are taking this path forward in terms of developing silicon spin qubits. Also, there is an approach in the field to integrate quantum and classical devices into industry standard nodes. For example, the work of my team back in 22, showing in 40-nanometer node the integration of classical, analog, digital, and quantum electronics. Good. So just to show you a couple of results from my team to get you an idea of where quantum motion is going. Particularly, our approach is to use industrial fabrication processes to enable that scale-up. We use IMEX 300-millimeter line, and we work in partnership with global foundries to leverage industrial fabrication processes. Particularly, on the IMEC platform, we've been able to demonstrate for the first time in a 300-millimeter wafer process, particularly an MOS process, a 2-qubit gate in silicon. This is a schematic representation of the device that we made. So this very much looks like a transistor, MOS structure, metal, oxide, and semiconductor, where we can isolate individual spins, particularly this is a 2-qubit system, and create our sensors, which is basically a quantum dot coupled to a reservoir. With our sensors, we can detect exactly how many charges we can isolate in this double quantum dot system, and particularly we studied a region where we have one electron in each of these potentials to project them into a single one potential with the 0-2 charge configuration. So, quick flash of the result. So this is a particular 2-qubit gate that we've implemented by making use of the exchange interaction between two spins that can be controlled by electric fields, particularly this detuning potential. So you see here the effect of detuning and the time in which we are activating that gate, and you see these coherent oscillations between the two spin qubits. You see the strength of the exchange interaction as a function of detuning, the coherence times, and the quality of the gate, which is on excess of 10, so we can perform 10 operations before the system actually decoheres, which is in line with what you will expect in natural silicon. This will only get better when we move to silicon-28 systems. Good, and finally, a result on industry standard processes. So this is our collaboration with global foundries that we've used to rapidly characterize more than 1,000 quantum dots, integrated silicon quantum dots, in their industry standard process. Good. So one of the mottos of the field is that as quantum devices develop, we need to rapidly acquire data to provide a statistical improvement. It's not good enough to have a good qubit. You want to have many good qubits reliably every single time. So several techniques have been developed out there to characterize as fast as possible as many qubits as you can. For example, Blueforce, in collaboration with different partners, is developed a cryogenic prober that allows you to characterize at 1 Kelvin in this particular demonstration up to 900 devices in a day. What we've done with Global Foundries is to develop a cryogenic multiplexer in which we combine digital, analog, and quantum electronics on the same chip, sits at the bottom stage of a dilution refrigerator, and allows us with fast measurements to characterize these many devices in just 5 minutes. Good. So, as I said, we combine analog, digital, and quantum electronics. Digital, that part is a high-frequency cryogenic multiplexer that is integrated on the same chip. We have superconducting LC resonance circuits that sit outside this chip that allow us to perform time division multiplexing. And the quantum devices are transistors embedded in this chip that allow us to capture individual electrons. Good. So this is a schematic representation of how our multiplexer looks like. So we have the different cells, and in each of the cells, there will be a transistor where we are going to have our quantum device. Good. Wrapping up the presentation, you will see that we can capture this is a cross-section of a silicon transistor where we can capture single electrons in that potential under the gate. And in combination with LC circuits, radio frequency reflectometry, and the switches, the cryogenic multiplexer, we can access these devices and measure their electrical properties. These diamond-shaped regions are the characteristic signature of electron trapping on these individual transistors that come from an industry standard node. So by repeating this process over the many devices that we have in our multiplexer, we can construct statistics. We can actually determine what are the physical dimensions of the transistors that provide the highest chances that you will get a good quantum dot. You can see examples of good quantum dots where you see that diamond-shaped region, but the examples of bad and multi-electron quantum dots. But what we can do is correlate the good quantum dots with the physical dimensions to tell us in which direction we should go. Good. So with this, I would like to conclude and set a few messages. First of all, that silicon-based quantum computing is making substantial progress in the last few years, taking the technology above the error correction thresholds and scale up to 6 qubits. In terms of scaling, industrial fabrication processes may be the key to enable this large-scale integration. And at quantum motion, we are taking that path. We are utilizing 300 millimeter wafer scale processes, and we've shown 2 qubit gates for the first time in a 300 millimeter process, MOS1, and we have combined analog, digital, and quantum electronics in an industry standard process. So with that, I would like to conclude and say that maybe the future will still look like silicon. We will still have a silicon revolution, but in this case, a quantum one. Thank you.
Thanks a lot, Fernando.